Hi, we're Autonomous Meteor Detector and Tracker Group Number 9. I'm Eric, and included in this project is also Jasper, Zhiwen, and Cameron. Our client for this was Dr. Chris Hurd, and our technical advisors were Nick and Steven. Meteors are elusive events. They're hard to track, and when we can track them, we want to know where they end up. The current system that's used is called the Desert Fireball Network, and while it's great, there are some pain points that we've identified that we wanted to rectify during the course of this project. One of the pain points is the current cost. The system right now costs around $6,000 to make. We designed and built our system for under $200. Another pain point is there's currently no AI being used within all the images that they capture. After all these images are captured and sent to the server, they must be manually sorted and labeled. We aim to create an AI model to be able to do that autonomously. The final pain point that we wanted to address is obstruction detection. There are points where a camera can become obstructed, and the user of the camera would never know until after they looked at all of the images. We decided to create an algorithm to detect those obstructions and notify the user. Our one goal for this entire system is to design and build a safe system for autonomously identifying and tracking meteors that is affordable, durable, and open source. And we have accomplished that goal.
So this is what the AMDAT looks like when it's deployed. You can see the housing is on a tripod, door is all shut, and inside is the Raspberry Pi, camera, and charging cable all snuggled up nicely. The screws are inserted in here. And this is a weatherproof AMDAT system ready to go and find some meteorites. So these are the different housing iterations of the AMDAT. All of them are 3D printed on Prusa Mark IV printers out of PETG. This is to inspire the open source nature of this project. We wanted people to be able to make their own improvements to the housing and manufacture it cheaply. This first iteration was simply a test print, just to see if that groove where we wanted the acrylic plate to fit in would work. It also has a hole for the USB-C charger to go through. This second iteration, we added this door on a hinge, which has the other side of the groove for the acrylic plate to fit into. This is just print in place. You shouldn't have to do any working with it to make it work. This version, we wanted to test making an actual seal, so we tried different versions of these fasteners here. We found that these small brass inserts work really well, and we also added this liquid silicone here to form a nice seal when the door is shut. So all you do is close it like that, put a screw in through here, and secure it tightly. We also wanted to make sure that the AMDAT housing can fit nicely on a tripod. So the original design involved these two pieces that slide into one another. However, we soon realized that that was more complicated than it had to be when you can just put a screw hole in the bottom of the material itself, which leads us to the last version of the AMDAT housing. And you can see again, we have the grooves, the door on a hinge, the brass inserts, and we also realized that you can't have a hole in the side of your project without water getting in. So we made this. This is a small cap for the USB-C charging hole. And that is the final design of the AMDAT housing. So this is a closer look at the cap for the charging cable. This was just a test print as a proof of concept, but essentially this one piece just pulls out of here. These round cylindrical pegs work to fasten the piece in. And to use this, you simply take your USB-C charging cable, put it into the housing, take the other piece of the cap, and secure it shut.
Our device is programmed to use the internet, so that means we can place the device wherever you want as long as there is Wi-Fi. So the way to set up the device is very easy. All you need to do is to connect the internet to the power. After the operating system boots up, a script will run automatically, and when the script runs, it will first guess its IP, and then based on this IP address, it will get its geolocation, and based on the geolocation, it will calculate when is the sunrise time and when is the sunset time. So if it's nighttime, it will keep taking long exposure images, so the trajectory of the meteors can be observed clearly. After that, the device will transmit the image back to the server. along with the metadata of the image, which includes like when and where the image was taken. Besides all this, we also used a sensor to detect whether the camera is blocked by any objects. How it works is that the sensor will shoot a light and it will calculate how long it takes to wait for the light to bounce back. So if the time taken is greater than a threshold, then we would take it as there's something blocking the camera. And this information will be sent back to the server and displayed on the web page. So right now, I'm gonna restart the Pi, just like it's just connected to the power. Okay, so the device has finished rebooting. So right now, a script is running automatically by the device. So if I put my hand on top of the sensor and the camera, we should be able to see an image of my hand on the server, and also an error message saying that the camera is blocked. So we have the image of my hand here, and also if we check the status, it says the camera is blocked.
Hi guys, I'm Jasper, and I'm going to talk to you about the AMDAT website. So let's pop over there. You can see we got a little notification here saying that camera 2 has thrown an error, and the error is obstruction detected. So we'll talk a little bit more about that in just a sec here. But the dashboard here kind of really provides all the information that a typical user would really need to view on a day-to-day basis. So we got our dashboard with our detections that we'll talk about in a sec, our camera info, and as well as the actual camera list the cameras themselves on the sidebar here. So let's jump into the sidebar real quick and take a deeper view of that. So the sidebar houses all the cameras that the user currently has access to. So that includes information like the status and whether or not it's connected. So you can see camera 1 here is disconnected, and that means it just hasn't sent a message to the server in a long enough period of time for the server to label it as disconnected. Maybe the user unplugged it and it's the expected behavior and we can go on happy about our day, or maybe something's gone wrong with its network and we want to go check up on that further. The next message we get here is from camera 2 that actually we have a status error here, which is obstruction detected, as we saw in the little notification before. And it's connected, so we're good there, and we just want to get rid of that status issue. So let's say we move Zhiwen's hand out of the way, and now our camera is no longer obstructed, and its view is perfect of the night sky again. So we can go ahead and reset on that, and we're back to a good status. The choice for making this a manual reset rather than trying to do it programmatically was because if the system runs into an issue that's large enough that it should report it back to the user, such as an obstruction or overheating or something like that, we want to make sure that the human intervention actually occurs. And then once that's occurred, the user can go ahead and say, yep, I did a thing, I reset the camera, and now I'm good to get status back to good and keep on moving along with my day. So with the camera sidebar out of the way, let's move over to the actual part of the dashboard here, which is our main view. And in here we've got a lot of info. We've got the actual um, detection of on an image, as well as a lot of metadata about that. So to view what it kind of looks like when we have detection on an image, let's move a test image into our server images directory, which is where the pies would all be publishing their images. And let's pop back over to their website here. And a script on the server is going to run in the background every time there's a new image in there and see if there's an actual detection. So we'll let that do its thing. And while it's doing that, I'll talk you through the metadata that we see for each of the detection images here. So the first things here that we get is the camera, so we know which camera it came from, which is super helpful if you have multiple cameras going like we do here. The next piece of info we get is the data was detected and specifically the time. The time is super important because the researchers that are doing the trajectory calculations as well as the orbit calculations of the detections, the fireball detections we're doing, use that info to actually line it up with other images and then do some triangulation and do a whole bunch of fancy math that I don't understand to calculate trajectory and orbit and all that good stuff. The next thing we get is location, which is super helpful if you had multiple cameras in different locations, so you can see where in the world this actual camera is detecting its objects from. Lastly, we have camera logs, which isn't super helpful to the average everyday user. Most people aren't going to care about this, but it's still nice to see that our system's running relatively normally and that there's nothing going on crazy behind the scenes. And then lastly, if this big red bounding box here is for whatever reason obstructing your view of the detection and you wanted to view a clean image without it, we could say view raw file, view raw file, and that would put us right where we want to be, where the thing is gone, but it's still the object detected picture. So let's see if that image got uploaded. And indeed it did. Here we go. We got a fireball detection right here on our test image from before. You can see it. Maybe it's a little obstructed. Let's see it better. There we go. Boom. Fireball right in the upper left-hand corner. Great. We're good to go. The system is working, and that's a detection for you. And the last thing that we have here is a gallery view. So this houses all the different images that we have in our entire data set, or all the images that are housed on our server right now. So this isn't useful for most average everyday users. They're not really going to look at this. But if you were doing something like making a data set to do object detection like we did in this project, then it would be helpful in order for you to actually see, okay, here's all my data. Let's scroll through it. Let's grab some good images, some bad images, and we can make a nice, clean, and balanced data set. And this page will dynamically load, so we're not loading all these images, which can be hundreds or thousands, onto the user's server, or sorry, user's website all at once. So that's a great overview of our dashboard. That's kind of what happens, the user interface part of it. I hope you guys enjoyed our project. I hope, thank you for taking the time to look at everything, and have a great rest of your day. Thank you very much.
Man, I can't see any of these meteors. If only I had an autonomous meteor detector and tracker. This phone's garbage.